This is a quadratics review in a precalculus course. I wanted to go over an array of topics that may and should be reviewed for you at this point in your mathematical journey, moving into precalculus. You've already seen parabolas, I suspect, and certain features about parabolas. I did want to cover a little bit of complex numbers because as we move towards the quadratic equation or the quadratic formula, we may have imaginary numbers as we've solved. So I wanted to just review a few skills with complex numbers. Factoring is also a skill that you need to have mastered at this point. Solving quadratic equations, there's several techniques for solving quadratic equations that I wanted to highlight, and also just a brief quick review about vertex and intercepts. We will be reviewing this more as we move forward to get in more depth and understanding between the relationship of the equation, the function algebraically, and the graph as we look at those. But I wanted to do some reminding. So I'm going to start with the review for complex numbers. Complex numbers, as you remember, involve the imaginary number I, which is the square root of -1. And so what that brings us to is complex numbers, where we can have a combination of a real and an imaginary number. And so what we've conceptualized in mathematics is that we can express that on a real and imaginary Cartesian coordinate with real and imaginary, where the coefficients of the real and imaginary parts can be expressed as a point on that plane. Okay, so that becomes important as you move forward into the physical sciences. For instance, I see it in circuit analysis. Adding and subtracting complex numbers, we'll be using that skill as we look at multiplying and dividing complex numbers. And just reminding that don't get confused when you add these. So I'll get -2 minus 2 plus 3i plus 3i. So I'm just going to combine terms like I normally do for, and I'm going to treat that I as if it was a variable, right? So this would be a 6i. Sometimes I see students get confused or forget the context that they're in, where that's not 9i squared. I just am adding those two terms. What I'm going to notice is I'm taking something and subtracting the same thing, so that should equal 0. And you can, distribute your negative and add that out, but I just want you to recognize like bigger patterns, right? When I see a thing and then I subtract, it's the same thing, I should get 0. I don't have to do the little bits of mathematics in there. Multiplying complex numbers involves multiples or exponents of I. I squared, I have I squared up here, and that is most frequently what I will see used. I did put what the I cubed and I to the 4th is up here, but more frequently I'll see I squared, and reminding you that I squared is -1. So if I do 3i times 5, I'm going to get 15i squared, but I know I squared is -1. So I can put a -1 in there and get -15. So you may just skip this step. I think you could skip that step if you become fluent enough in I squared. I don't need you necessarily to show the work there. To review, this would be 6i plus 9i squared. So I would change this around and put it in complex number proper form, -9 plus 6i. This last one, we're going to do this again in a couple more slides, a couple more times. I'm doing a difference of squares. I don't know if you see that. This is a special product. We'll be working with special products as we move towards factoring. But when I multiply a complex number by what it is complex conjugate, I'm going to use even not knowing that, I can do the difference of squares here. 4... or I'll say 2 squared minus 3i squared, right? That's the difference of squares. That's where that term comes from. So I'll get 4 minus 9i squared, which will be 4 plus 9, which is 13. And I'm going to highlight right here, watching a few slides, we like this technique because it results in just a number. It's not a complex number. It's a purely real number. Dividing complex numbers and with complex conjugates is where I see students still struggle when they get to precalculus, even if they've done well in math up until this point. This can still be a struggling part because you're you're doing rational numbers, analysis on rational numbers, and you have I in there. So what the convention is when an imaginary number is in the denominator, mathematicians lose their mind or something. I'm not sure exactly. There's the convention where we don't like I in the denominator, much like we don't like radicals in the denominator. So we use a complex conjugate or multiply by I in order to get a pure real number in the denominator. So in order to do that, like I said on the previous slide, if we multiply by the complex conjugate, then we can have just a pure real number as the result. And the complex conjugate is not taking the negative of the whole thing. It's taking the negative of only the imaginary part. We're going to negate the imaginary part of a complex number. So you can see that if this is the original complex number, its complex conjugate has a negative sign. We negate whatever the imaginary term is, only in front of that imaginary term. So I have an example here just to go over that real quick. -5, find the product of -5 minus 3i and its conjugate. So the first step you have to do here is identify the conjugate. So I'm going to write down this. I know I'm going to multiply that, and then I'm going to have to multiply by the complex conjugate. So I'm going to negate the sign in front of the I term, which is negative to begin with, so I'm going to make it positive. There's opposing signs in front of that. I do not change the negative sign in front of the 5. That is not the complex conjugate. That's the negative of it, but not the complex conjugate. So what I'm going to do is a difference of squares here. I'm going to take -5 quantity squared, and then I'm going to subtract off 3i quantity squared. Okay, I don't need a parenthesis on the end there. So I'm going to get 25 minus 9i squared. I'm going to remember that I squared is -1, so I get plus 9, and that's 34. So that's how you would do that problem. Let's divide by a complex conjugate. This is where students get a little off the track still at this point, like I mentioned before. In order to get rid of an imaginary complex number, a complex number in the denominator, I'm going to multiply by its complex conjugate, and that'll give me a real number in the denominator. But remember, I don't want to fundamentally change this expression, so I need to multiply by a whole factor of 1. So that's why I'm going to multiply by -6 minus 4i over -6 minus 4i. Need to multiply it by in the denominator, and the denominator tells me what needs to go in the numerator because I need a factor of 1 overall. Those two things cancel out to 1. So I'm going to go through and I'm going to multiply out the top and the bottom and simplify from there. This takes a few more steps. Watch out and be precise with your algebra and your mathematics in here. There's some negatives floating around, and so don't lose or multiply too many negatives. So I get -30 plus 42i minus 20i plus 28i squared. So I FOILed it out. I did first, inner, outer, right? That technique. On the bottom, I'm going to do my difference of squares. I'm going to get -6 squared minus 4i squared. And I will be able to simplify that. So the top simplifies to, what do I have? 28i squared is a -28. So I get -30 minus 28, which is -58, is my real part of that numerator there. And then on the imaginary calculation, I get 42 minus 20i, which is -32i. I'm going to put that over the bottom. The bottom is 36 minus -16. 36 minus -16 is a 52. All right, so -36 minus 16i squared. I squared is -1, so I get 36 plus 16. All right, so that is working through the mathematics of those imaginary number multiplication. I still need to simplify from here. Not much is going on other than a factor of 2. 58 divided by 2 is 29, so I'll get a negative 29 over 26 plus 16i over, I do some math wrong? I did do some math wrong. This should be 22i, right? Maybe you all saw me do that and didn't say anything because I can't hear you. Okay, so 11i over 26. So that would be the answer to this problem if you're working anything. Just a reminder how to do that. One notation note I noticed when I was practicing this problem earlier is I put the I next to the 11 on front. You may see other places where they put the I like behind the whole fraction. It's arbitrary to me. It means the same thing to me. A mathematician might get a little bit more particular about notation, but as a physicist, as long as the I doesn't look like it's under a radical, I'm happy with it. Why am I reminding us about imaginary numbers? It's because sometimes you're going to solve the quadratic formula and you're going to end up with an imaginary number because you'll have a negative number under that radical. So you need to be able to know how to deal with those situations and recognize what to do in that situation. When I'm going to know, I graph this parabola. You're not surprised that I graphed the parabola. And what I notice about that is that this function, this blue line, never equals 0. It never equals 0. So that's what the solution to the quadratic formula is going to tell us, is if we get an imaginary number as a solution to the quadratic formula, then we're going to have a no solution situation. There's no solution for when this parabola crosses that x-axis. So hopefully that's a good review for complex numbers. I'm going to keep moving forward to factoring quadratics. How to factor involves how to undo polynomial multiplication. And in the simplest situation is working with an x squared term, where you just multiply a linear term times a linear term, and then you get a quadratic formula, form sort of way. You should have covered this before this point when you get to precalculus. I'm doing a review of common techniques that I see that you should have quick to your disposal to be able to factor. The first thing is factoring out a common term. This may be just a constant, 3x squared minus 3x. You can see factoring out a 3 out of both of those terms. The other thing is to be able to factor out a variable term, right? You may see that I can factor a 3x out of both of those terms. That would leave me an x minus 1. So being able to factor out a common term, just a simple common term out of all of the terms in the polynomial. Grouping, I think, is an important thing to keep in mind, but I don't see it used very frequently. It may be a strategy that you use as we move through the material, but I don't see it very often. But we're going to remember it's there. Every once in a while, we're going to remember it's there. More frequently, you're going to be factoring trinomials where a equals 1. Remember the general form for a quadratic is there's an a out front, but we're going to let that a equal 1, and this is the simplest, nicest way of factoring polynomials or quadratics, right, is just when there's a 1 out front of that number, and then you just have to worry about b and c. So what I remind people at this point is these strategies for how to split up a trinomial, or how to figure out what were the two numbers that made up C, right? C is a combination of integers, m and n. They multiply together to equal C and are related to B. M plus n have to equal B. M plus n has to equal B. All right, so at this point, you learn some common strategies, factoring by grouping. There's a box method where you can just like multiply things together to see if they match. There's also the diamond method where you can put your A and your C in, and AC goes up here and A plus C goes down here, something like that. Or B goes down here, right? B goes down there. So that's the diamond method. I frequently don't use the diamond method, but I know a lot of people who like the diamond method. I'm more of a box method person, or I just check on a graph at this point. You may be just used to checking on a graph at some point. Trinomials where a is not equal 0. This is again a point in the curriculum where I see even the best students in precalculus or math before this struggle when there's an a out front when you're factoring your trinomial, and you end up with something like 3x plus 2 times 2x plus 3 or something, right? Where if you multiply this out, you get a 6x squared out front, right? The 3x times the 2x. So factoring becomes more difficult when you have to take two things into account rather than just the one c on the end. So again, there's an array of strategies for being able to solve. At this point, I have a few examples that I think you should be able to do. I'm not going to go through strategies necessarily, but I want you to be able to do these. This A should be pretty simple for you. What factors of 24 add up to 10? You should be able to do this almost in your sleep at this point. This one where I was mentioning that you have a factor, an A out front, A is not equal to 1. So I'm going to tell you that this factors, and then you have to figure out in what way does it factor. There's ways I can make this easy. I see this is a plus sign and this is a plus sign, so there must be a plus sign in the middle of both of the terms that it factors to. And I see a 3 here, and the only factors of 3 are 3 and 1. So I know that has to be 3 and 1 on the end, and there has to be an x here and here. And then you go through and you play this game. So what factors of 6 when it multiplies by 1 and 3 gives me this result of 11 in the middle. And so there's a couple of options, right? You have 6 and 1 and 1 and 3, or 1 and 6 and 1 and 3, 2 and 3 and 1 and 3, or 3 and 2 and 1 and 3. So you see all the possible combinations that go in here, and you're going to identify the one where they multiply together and then add to 11 in the middle. So I see 2 plus 9. So I know that there has to be a 3 multiplied by the 3. So a 3 goes here, and then the 2 multiplied by the 1. And so that's how that would factor, right? You play this game, and you saw how I did it. I did it kind of like the box method, but I also went through, I might have done it just quicker in my head, right? I wouldn't have said all that aloud if I wasn't teaching someone. Another thing that I see students get messed up, I won't say messed up on, but they make work harder for themselves rather than smarter because they haven't put to memory the perfect square heuristics. There's the perfect square binomial where I just square a binomial and I get a perfect square of it, and it results in this formula, right? I have a squared plus 2ab plus b squared. So if you're factoring, if you recognize this form, and that's what I see students really haven't put memory yet, is recognizing this form. When I go to factor, one of the first tests I'm going to do, especially if I have a plus or minus there and a plus there, is just to see, is that a perfect square? Is A a perfect square, and is B a perfect square? And is the middle 2 times a plus b, right? That's the test you would do. Then I'm just going to factor it super easy. I'm not going to go through any games to factor it. I'm just going to remember, oh yeah, that's how that factors. Work smart, not hard, right? The other thing I'm going to remember is the difference of squares. I mentioned this before. When I have a difference of squares, I'm just going to remember that that's what it factors to. I'm not going to play any games or go through any work to remember that that's what it factors to. So I have some examples here I expect you to know pretty immediately when you look at them that it's going to have a special products solution. Well, I'm going to have you note here the plus sign here. This does not factor at all. This factors actually into imaginary numbers. So if you were moving forward, you could factor it into imaginary numbers, but as it is as a real number, it does not factor. So this would be a DNE situation. It does not factor. Does not factor real. All right. I may move to another part of some sort of curriculum where we would be using the factored imaginary version of it, but I'm not going to cover it here. Whereas this, where I have a negative sign here, that is a difference of squares. Note, like, words mean things. I need a difference of squares. This is an addition of squares. I need a difference of squares. So I'm going to say this is x plus 10 times x minus 10. Done. I don't have to, I didn't play any games getting into that other than this is a special product. Over here, I'm going to notice that this is 25x squared. That's a perfect square, 5x. I'm going to notice that this is 4 squared. 16 is a perfect square. And then I'm going to notice in the middle that this is 2 times 5x times 4. That's 40x. So when I do this, I'm going to recognize that this is just going to be 5x minus 4 squared. Done. I'm not playing any more games on factoring that other than that. I want to move forward in the material to solving quadratic equations. Now that we've reviewed sort of solving, factoring, some sub skills to this, move up to a little bit higher skill of solving quadratic equations. I want to remind and introduce to you maybe that I called this a review, but I think I'm introducing, remember that there's a factored form. For all quadratics, when I have this form, it came from foiling two things. What I'm going to mention is not all parabolas in this form can be easily factored. If there's decimal going on, if they're like, it's not easy sometimes, but you can always write out a factored form. And there may be situations where, say, like if we have integers in here, if we have integers for x-intercepts, all right, it's going to be easy to write an equation, just as easy to write an equation for the quadratic form as it is with a transformation, all right? So this parabola can be expressed in these 3 different ways. And sometimes we're given different forms, and we need to be able to work with them, or we need to come up with these different forms. Like, how do I get information from a graph in order to write one of these forms? A lot of times if you're given a parabola, the vertex form is going to be easy. For instance, I move over 2 here and down 4, so it'd be easy to write out the x minus 2 squared minus 4 part of this function, right? And then I'd have to do this test. I need to still figure out what this a value is, right? But I could write that out. Another thing that I can do, what I'm going to do is say, oh, there's a factored form f of x where I can multiply a times an x minus something and a times x minus something in order to get the same equation. It'll be the same equation. Which isn't too hard for this problem. I see one x-intercept, that's what goes here, is the x-intercepts. I see one x-intercept goes through the origin, so that's the 0. The other is 4, so I'm going to put a 4 here, and that would be a base for writing that equation out in factored form. So you're seeing that other forms other than the general form are useful. What are the useful forms of our parabola? We're going to keep that in mind in our theme of working smart, not hard, as we move forward. Solving quadratic equations, there's typical strategies for solving. Solving linearly often won't work. So up until this point, you were used to like solving an equation and isolating x. But if you were given a quadratic here, there's no way you can isolate x on one side and all of the other numbers on the other side. That doesn't happen here. So you need different strategies to be able to solve, all right? So I'm going to highlight 3 of them. I'm going to go over each one of these in detail and highlight that we are going to move more frequently, all the time, frequently, inspecting the graphs given any forms, any of these forms, all right? So what I want to remind you of is that quadratics have 2 solutions. And in a previous slide I mentioned sometimes they have no solutions, right? What's going on there? Well, we can see if I have a parabola, a proper parabola that's not limited on domain, it will cross the x-axis in 2 different points. And this power here indicates how many times we expect it to cross the x-axis. There should be 2 solutions, and we can see that here, a solution there and a solution there. What I'm going to note is in this situation, here's the x-axis here, and we're going to note that this parabola does not cross the x-axis, so we would get imaginary solutions to any way we tried to solve, and so that we're going to say does not exist, does not cross the x-axis, etc. So sometimes no solutions is a legitimate answer to solving a quadratic equation. Solving with a radical, here's some examples here. It requires arranging in the vertex form. I don't know if you noticed that this one is in the vertex form where I would have like x minus 0 quantity squared, all right? And then I have the minus k, or minus k plus k out here is negative 48, right? So the way I would answer this, I divide by 4 first and get x squared minus 12 equals 0. And then you can see I can solve with a radical. If I have x squared, then I can say that x is the square root of 12 and do a plus or minus. Remember, we want two solutions. So you remember when you're doing this, it's a plus minus situation, plus minus. Okay, so that's with a radical. I think that's pretty simple. This is a situation where this is not possible, right? If I divide by 2, I get x squared plus 45 equals 0, x squared equals negative 45, and all of a sudden, in order to find x, I'm taking the square root of a negative number, which isn't impossible. We know how to do that, right? But then I get an imaginary number, and remember to put the plus or minus out front, and that can't be a real solution. So that's what's going to tell me that I have no solution in this situation, a DNE situation. And also, I would verify these on a graph. I would verify both of those. I would make sure that this upward pointing parabola does not cross the x-axis, and also I would inspect the graph of the upward facing parabola here so that I notice that plus root 12 was a solution and negative root 12 was the solution. It's probably some decimal, right? 3 point something. But I would make sure that it's 3 point something. That's what I would expect my solution to be. Solving quadratic formula. Okay, so you've done this before. I know you've done this before. You identify A, B, and C in your problem into the A. The B, don't forget the negative sign. Sometimes I see students get sloppy in here and forget a negative sign when they're identifying their A, B's, and C's. Okay, so make sure you identify those accurately. Algebraically, you can solve. And then, like I said on the previous slide, I would graph it and then inspect the graph for what that x-intercept is based on, what I get in my calculator and what I see on the graph, and they're decimals. That's perfectly fine. You can have a decimal. That's fine. What I'll mention about the quadratic formula is that it's reliable and it always works. It is reliable and it always works. If you look at that and you don't know if it factors, if there's decimals going on, you can always identify your A, B, and C and put it through the quadratic formula here, and you'll always get your answer for solving a quadratic formula that way. But for me, it's not always a work smart, not hard situation, because sometimes you can factor them. Sometimes you'll be using the work smart, not hard situation when you know a problem factor, solving by factoring. So when I look at solving by factoring, I'm going to arrange in order, right? I'm going to go from highest power of x down to the lowest power of x. This is x to the 0th. This is x to the 1st, right? Anything to the 0th power is 1. So we have that constant term on the end. We're going to factor fully using common strategies, which I kind of hand waved in a previous slide in this lecture, but using common strategies. And then what we're going to do is we're going to use the zero product property. I don't know if you remember that technical vocabulary from a prior course that you've done before, but the zero product property says that if I have two things multiplied together and they equal 0 multiplied together, then either one of those things is equal to 0 or the other thing is equal to 0, because that's the only way I can get 0 is if I multiply by 0. So I can't multiply two things and get 0 otherwise. So one of those things has to equal 0, and this is convenient if possible. If possible, it's convenient, but most situations aren't integer values, especially as you head into the sciences and you're dealing with real data, etc. You won't be able to do this. I did want to cover an example for this section, solving by factoring a polynomial. I know this is not a quadratic. I know this is a whole lesson on quadratics, and I picked a non-quadratic polynomial. You may notice, though, it says solve. Give your answer separated by a comma. That's a notation thing that if you plug it into a computer for solution evaluation. But what I want you to notice here is there's some factoring going on. Right away, you see there's some factoring going on. There's definitely an m. You see an m. If we want a quadratic, we want just the 12 by itself, so I can factor an m out. And even better, when I look out front here, I see this is a 3, and I can factor a 3 out those other coefficients. So I'm going to take a 3m out of all of those things. That leaves this an m squared plus 5m plus 4 equals 0. Okay, so you see how this is a quadratic. It's factoring quadratics, so you're used to this. This is the skill that I'm emphasizing by factoring. So let's factor it. I'm going to notice that there's only this nice little 4 over here, and the factors of 4 add together for 5, and I have a plus sign here, so I can factor this easy. M plus 1 times m plus 4 equals 0. So that's factored. Now I can solve with my factors. So the zero product property says 3m equals 0, or m plus 1 equals 0, or m plus 4 equals 0. All of those could be a solution, right? Any of one of those could be a solution. All of them could be true, but only one of them need to be true. So I could say m equals 0, or m equals -1, or m equals -4. Those are the solutions. If I would enter them in a computer with a comma separated between them, I would put them in like that. Another way to enter these might be on another different type of formatting problem would be like, what are the x-intercepts? So you would say 0, 0, -1, 0, and -4, 0. So when I look at this graph, and you may note that I have this little white thing down in the corner, the graph, of course you know I graph this. You know I graph this. Of course I graph this. Hopefully you are getting into the habit of graphing for yourself. And look at that. Wouldn't you know? When I factor this, I got all of the x-intercepts. And note that the factored form, this factored form, can be easily written if I know the x-intercepts. So hopefully when you're looking at this and you're noticing what I'm highlighting is that I factor it down and that'll tell me the x-intercepts. But if I look at the graph and I see the x-intercepts, I can write that original function on some level. That is very powerful because what you're learning is graphs give us much more information. We see the texture of a graph, we see intercepts, we see symmetry, we see minimums and maximums. There's so many things we see on a graph that we can't get out of a algebraic expression, right? So if you're given a graph, knowing how to read the graph and create that algebraic expression is a very powerful tool, very, very powerful tool. The last thing I wanted to talk to you about in this lesson is quadratic functions, their vertex and their intercepts. So we have been solving, when you solve the quadratic function set equal to 0, you're going to find the intercepts, right? So we're going to look at those a little bit more in depth, all right? Keep going in depth. And you may have seen this before. You may have seen it and touched on it. You may know it already. You may have not seen it, and that's why I'm covering it, is I'm concerned if you haven't seen it. And there is a few things I'm introducing and emphasizing as we move forward, which was this factored form. Remember, there's always a factored form. And so I think also if I wanted to, I could put an A out front. I do believe properly there should be an A out front if there's an A here and an A here. All right. So quadratic form, just to remind you that there's 3 different forms for me. You may know the 2 top ones very intimately, but I am really going to emphasize and remind you about this bottom factored form, especially as we head into polynomial functions and we head into rational functions. Having a factored form is going to tell us asymptotes and intercepts and all of that stuff. So let's move forward on this. I'm going to remind you with the general form, we can calculate the vertex. If we're given the vertex form, that's the most convenient form for a parabola, right? Because then we can just read off the vertex h comma k from this h comma k. So like in this situation, h comma k would be, what is that, -2 comma -1, right? But if we were given the general form, just an A, B, and C in a general quadratic form, we would know how to find where the h of the vertex is, and then once we know that h, we would plug it into that function, and that would give us the y value, the k of the vertex. I don't think there's a direct way to get the vertex from the factored form. The factored form is much more interesting in terms of intercepts rather than the vertex. I can solve for intercepts, so I covered this before. We're going to find the vertical intercept where it crosses the y-axis, the vertical intercept. So you can see on this example, it's 0, comma 3, right? When I plug in x equals 0, right? X equals 0, then I get 3 out. And you're just plugging into the function, whichever form you're given, wherever you see x, you're going to put in 0. So that would give you the y-intercept. The x-intercept is solving the quadratic, and so I covered that in a previous lesson, short mini lesson on how to solve quadratic functions. Write an equation for the quadratic function shown. Let's do this. I didn't solve this before for practice, so I'm kind of shooting from the hip here, but I like this. I like this one. I'm going to identify the intercepts in here. You all identify the intercepts in here. We have, is that a -1? It goes exactly through -1 on the y-axis. Beautiful. What I'm going to note is there's a vertex here. So when I'm given a graph, maybe what you're catching on, your monkey mind, your primate mind is catching on from me is when I look at a graph, I'm identifying key points. All right, identify key point. So those are the intercepts, and those are the inflection points, minima, maxima, right, important points. So those two things, I call them inflection, but it might not be an inflection point. This is a minimum or a maximum. I'll just put min or max on here because we're dealing with quadratics. We're just going to have a min or max. So I'm identifying those key points in here. They're going to tell me things for how to write an equation. That's what I was talking about a slide ago. How to write an equation given the graph. Just given the graph. What am I seeing here? Well, for me, I think it's easy to do the vertex form. I move backwards 2 and downwards 3. So I could write f of x equals a x minus -2 squared minus 3. All right, so remember there's in the general form there's a minus here and I have a -2, so there's 2 negatives. So that would give me that. I could solve for the a value by plugging in a point. I'm going to note I have the point 0, -1, right? When x is 0, y is -1. So -1 equals a 0 plus 2 squared minus 3. I am going to move the 3 over, so I'm going to get a positive 2 on this side, a times 4, and a equals 1/2. I can solve for it algebraically. What I'm not going to do is assume that it's just x plus 2 quantity squared minus 3 and be done with the problem after I identify the vertex here. I need to assume that there is some sort of coefficient a out front, and indeed when I plug in a point I see that there is a coefficient a half out front. All right, so this is going to spread it out, right? I'm going to have some stretching on the parabola that's going to make it not go as fast upward as I normally expect it to. I'm going to multiply the output by a half, right? So write an equation. I think I'm almost done. Here's an equation. F of x equals 1/2 x plus 2 squared minus 3. Done. I think that's one way to write this equation. So again, you can see what I'm saying about identifying important features on the graph. When I say identify important features on a graph with a parabola, the intercepts are what I'm looking for, and the vertex, you may say like if it's pointing up or down, those sorts of features are important when you look at graphs and behaviors on graphs and how they correspond to the algebraic expression.